Shown here is an isomer of the structure of water hexamer known as the book. The red arrow above the hexamer indicates the direction of the electric dipole of the cluster. If we then rotate to look down an axis, we can watch how the complex can undergo rotational motion. The rate of rotation for a given energy is determined by the molecule's moment of inertia along an axis, referred to as its principal moments. The rotation of the electric dipole will allow light to be emitted, as seen on the right, to produce a rotational spectrum. More complex rotations are possible. If we then substitute one of the oxygen 16 atoms in normal water shown on the top for an isotope oxygen 18 highlighted in yellow on the bottom, the mass distribution of the molecule will shift slightly, causing a change in its principal moments. Now when we compare the same rotation, we notice the substituted isotope log will rotate at a different rate than its parent due to the change in the principal moments mentioned earlier. This will cause a different frequency of light to be emitted when the molecule undergoes a rotational transition. Thus we can collect the spectrum of the cluster, and after fitting the shifted spectrum, we can determine the three-dimensional coordinates of the substituted atom by using Kreischmann's equations. This can be repeated for each of the atoms to find a full three-dimensional structure. Chirp pulse rotational spectroscopy has the advantage of being able to measure 6 different isotopes and their parent in a single experiment. Additionally, the incredible resolution of the technique can detect all 3 isomers of hexamer, book, cage, and prism, and their isotopes in one experiment as well.